Hi everyone, I'm Vitaly. This video is a lecture that I was invited to give as a guest speaker in Florida International University. And the topic is Introduction to Generative AI. So this is the outline of what I will be talking about today. First, I will talk about applications of generative AI. What is it and why we even care about it? Then I will discuss a formal definition of generative AI, how it is getting trained. And then I will discuss popular architectures such as autoencoders, generative adversarial networks, variational autoencoders, transformer-based models, and diffusion models. So what is generative AI? So from the name, it is easy to deduce that it is artificial intelligence that generates something. But how can model generate? So the important component is training. So imagine that we have a lot of pictures of cats, so millions of cats in the database, and the goal is to train generative AI so that it learns the distribution of this data such that it can generate samples close to this distribution. So the model will learn what cats looks like. So on the picture, you see the real generated images of cats that they generated using DALL-E 3. So once we know this distribution P, right, so the model is able to generate new examples of cats that we haven't seen before and which is close to our learned distribution P. So there's tons of generative AI applications. There's a prompt-based question answering, generating images, music, video, code, generating data for research, and preserving privacy. So the most popular right now is the prompt-based generative AI. ChatGPT is the most famous one here. The alternatives are Palm 2 from Google and Llama 2 from Meta. It can do question answering for you. So whatever you have some question, preferably not factual, so it still have some problems of generating facts, right? So it can just make up things. But it's doing great with something that requires logic. So the next application is generating content. I used it myself to write research articles, for example. So I still create the original content from the head, right? But before ChatGPT, writing a paragraph could take me like the whole day, right? So you need a perfect sentence in order for a journal to accept your paper. But now I can just give a rough draft to ChatGPT and it will polish it and turn it into a very good sentences. So only few iterations needed to create a perfect paragraph. So it is also used in solving assignments for students. I don't think it's necessarily bad, right? So it can be used in educational purposes. So let's say you're stuck with some some things and you want to know why. So you can provide ChatGPT your assignment and say, hey, I'm stuck here. Can you help me? And it can give you right directions. Say, okay, like you made a mistake in this part, like try this approach, and it also can direct you to a literature, like, hey, read this and this to get more knowledge. So I think it's great for this purpose. And yeah, it's good in explaining new concepts. So whatever you don't understand. So for example, whatever new article comes out, and if I'm stuck, I don't understand the math. So I just ask ChatGPT, hey, can you explain this to me as I am 5 years old? And ChatGPT is doing a great job in this. So Midjourney and DALL-E can generate amazing images and art. It can generate a logo for your company, illustrations for books and magazines, and also do basic design. So Photoshop recently added a new generative component that can augment your photos based on prompts. So for example, it can remove people, can change the background to something else, like, hey, add an ocean to my background and like give me some romantic vibes, and it's going to augment the whole image for you. So this is very, very good. There's a countless of possibilities of what you can do with images. There's generative models that can create music and videos. So here's the list of subset of such companies. People use it a lot for content creation. So now you can easily generate unique music and video for your material, which is unique, so that you don't have copyright issues. And they're usually like beautiful and sound very appealing, like especially beats, like jazz, electronic music. It can generate those. So whether you are a podcaster, blogger, or you create educational videos, all of it will be useful for you. You can also use it for advertisement to create ads, films, games. Again, a lot of applications. So another popular branch of generative AI is deepfakes. It is used to generate fake videos of famous people who do or say things that they never did. It imitates their voice and facial expression. So let's take a look at the example video here. This is a video of Obama making statement. So this video was created like 5 years ago. So let's take a look.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things. So, for instance, they could have me say things like, I don't know, Killmonger was right, or Ben Carson is in the sunken place, or how about this? Simply, President Trump is a total and complete dipshit. Now, you see, I would never say these things, at least not in a public.
So yeah, you saw how realistic the video is, right? And it was made 5 years ago. Can you imagine that? And imagine what AI can do now. So it can fake it as it is very natural. So there's no limits. Of course, there's misinformation concerns, right? So imagine having a video of Biden declaring war. So this can destroy the whole world, right? So we need to use these technologies with caution. And on the other hand, if it's not a malicious intent, it can be very useful. For example, it can be used in educational settings. So imagine Albert Einstein giving you a private lecture. So the lecture is just for you, saying things that is relevant to your background. He knows about you. So then it would be really great. So another useful tool is a GitHub Copilot. It can assist in writing code. So this is very relevant in my field, in computer science, and probably in your field as well, if you're watching this video. I personally never used it, but so for me, ChatGPT is enough. But I heard it's very good. So you can start typing something and the system auto-complete the function. So pretty amazing. In software engineering, it is great. So another application of generative AI is to generate samples to train even better AI. So it is relevant in biased data sets. So imagine a data, um, for example, for training self-driverless cars. So 95% of this data is images of sunny weather, right? So the car driving in sunny weather on a highway or on a straight roads. So it's relatively easy to drive in such scenarios, right? But what if, but what if there's some unexpected obstacles? So we want a model to be robust to outliers. So therefore, we need to generate some edge case scenarios. So what if a large plane is popping in the sky? So we don't want the model to freak out in those cases and just lose the driving abilities, right? It will be very dangerous. So we also want to generate examples of harsh weather with a lot of rain. So maybe in hurricanes, right? So there is a very small chance that there is a data on driving on in hurricanes because it's dangerous. Nobody does this, right? But what if you have to? So we generate hurricanes, fire, tornado, and so on, such that the self-driving cars would be ready for those scenarios. So we also need to generate a lot of instances of pedestrians with different poses, crossing roads in the most unexpected way, again, so that the model will be prepared. So only by generating those kinds of images, we can train the model that will be ready for unexpected things. In other words, we want to generate underrepresented samples to improve the performance of predictive model. So the applications are self-driving cars, weather forecasting, medical images, diagnosis, and so on and so forth. So another application is preserving privacy. So imagine that we are a hospital that has a lot of information on patients, their DNA, samples, blood, clinical data, tomography scans, and so on. So this data is very valuable for researchers and pharmaceutical companies. But hospitals can't give away this data because it is private. It is actually illegal to share it because you can track down each individual. So generative AI can be the solution to it. Using AI, you can learn the distribution of this data and generate samples as good as original. So it's going to have the same statistics, the same properties, but it's not specific to any patients because it's fake. So now you can generate those samples and let other people to use this data to either train their own models for statistical inference or for some other applications. Okay, so this was applications. So now we move forward to formal definitions of generative AI. So let's refresh our mind. As I said at the beginning, the goal of generative modeling is to take as input training samples, learn the underlying distribution, and then generate samples that are as close as possible to the original distribution. So generative modeling is the subset of unsupervised learning. So in supervised learning, we have both dataset and labels. And the objective is to learn a function that map input X to the output Y. So examples include classification, regression, object detection, segmentation, and so on. In contrast, in unsupervised approach, there is no labels. We have only data X without any Y. And you need to learn the patterns of underlying structure of the X. So for example, in clustering, anomaly detection, and the generative AI is one of those examples. So next, I will cover popular generative AI architectures. So for that, we need to understand the concept of latent space. So this is the key concept of generative AI, and actually in a lot of AI fields. So let's take a look at the example of autoencoder. So we have an input image X, and then the encoder transform it into a vector in some high dimensional space, which we call a latent vector. So then from this latent vector, the decoder reconstructed to the same image, right? So the latent space is basically the space of latent vectors, which are the abstract vectors that are transformed by some machine learning architecture. So here encoder can be anything. It can be convolutional neural networks or just fully connected layers, transformer networks, anything. So what is the purpose of that? So the input and output in autoencoders are exactly the same. Why do we even need those latent vectors? And the reason in this case is data compression and feature extraction. So we want this latent vector to be smaller than the original input image. And if the decoder is able to reconstruct exactly the same image, it would mean that this abstract latent vector contains all necessary information and useful features. So autoencoders is the way to reduce dimensionality, and then we can use this latent vector to train another model, maybe in supervised settings, and the latent representation is going to be more efficient because the data is compressed, so it has more information in less number of digits. So the latent space is learned during the training, which depends on objective function or loss function. So the objective function is kind of a way to signal whether the model is doing a good job or not. It's not, if it's not doing a good job, then the weights of the encoder and decoder are going to be adjusted such that at the next iteration, it will do a better job. So you provide a lot of training examples of the input image, and using the back propagation, the network is going to adjust the weights to generate latent vectors that optimally reconstruct the original inputs. So a simple example of reconstruction loss is listed here. It's simply the difference between intensities of pixels in the original and reconstructed image. And again, I want to emphasize that there is no labels needed for such training. So now imagine that your network is already trained, right? So it knows the underlying distribution, and so from input, it goes to latent vector and it accurately reconstructs the image. So then what? So what if we only use this portion? So going from latent vector to reconstructed image without any input. But we don't know what the latent vector is going to look like, right? So what if we set it to some random vector, right? So then would the coder be able to create some meaningful image? So we don't know. Probably not, right? So if you just create a random latent vector, then it's probably going to be just a noise. So the reason why we were able to reconstruct image is because we gave as input the right image, right? If we just set it to random, I doubting that is going to be something meaningful. So autoencoders are not useful for generation. but can we just change the training settings in a way that it would? So generative adversarial networks, or GANs, can solve this problem in the following way. So in the decoder part, we call generator, that aims to generate fake images just from random latent vector. And then we access a real image. So this is so here I'm describing the training part, okay? So we provide the real image during the training, and both of them goes to another network called discriminator. So the objective of discriminator is to classify the image as the real or fake. So both generator and discriminator are trained at the same time, and the loss function is consist of discriminator loss and generator loss. So generator is simply a reconstruction loss that tries to create the image as real as possible, while discriminator tries to classify it as real or fake. So it's trained at the same time. So generator tries to generate their image as real as possible, while discriminator is trying to classify it as a real or fake. So the perfect generator will be at the point when discriminator is not able to classify real versus fake anymore. So once we reach this point, we can just select generator, forget about discriminator, and just from the random latent vector, we will be able to create very nice images. Okay, this was generative adversarial networks, and the next class of generative networks is variational autoencoders. So on the slide, you can see the traditional autoencoder that we already covered. So the one thing that you notice is that it is deterministic. So once the model is trained and the weights are set, if you supply the same input image multiple times, the encoder is going to generate the same latent vector, and the decoder is going to reconstruct the same image. So for the same input, you're going to have the same output no matter how many times you run the model. But what if we want to generate many images? So let's say you provide input image of a cat, right? And you want to generate like 10 images that look similar to this cat, but kind of different. Can we do that? With this model, no, we can't, because it is deterministic. But with variational autoencoders, we can. So this model introduces the element of randomness. So now, instead of getting a latent vector, the encoder is going to guess what is the mean and standard deviation of this vector given the input, right? So this formulation is even closer to our original objective. We want to learn the distribution of the training data and generate samples as close to this distribution. So from input, we're going to learn the mean and standard deviation, right? And then in the generation part, it will create a latent vector that is somewhere within this distribution, right? And then it goes to decoder, and it will generate some image X prime. So basically now, instead of generating deterministic latent vector, we're going to guess the statistics, the mean and standard deviation, and then sample some latent vector from this distribution. So during the training process, we learned two sets of parameters, phi and eta. So phi is the encoder and theta is a decoder. So those are sets of weights in our network, and the loss function consists of reconstruction loss, that's the same as before, and plus regularization term. So this is what's interesting, right? So the regularization can consist of posterior distribution. That's the distribution of latent vector z given the data. That's what encoder generates, right? So it generates z given the input x. Okay. So, and the second term is the prior distribution. So this is the hypothesis of what the distribution of latent vector will look like. So this term d is essentially the distance between the encoding probability for generation and the prior hypothesis p of z of the latent distribution. So in practice, what we can do is we fix the p of z to the Gaussian distribution with the mean 0 and standard deviation 1. And then we kind of optimize the posterior distribution to generate the latent vector. So this is the intuition. To fully understand it, we need to go through the theory of Kullback-Leibler divergence, so for which we don't have time on this lecture. But if you're interested in it, check out the paper Autoencoding Variational Biases. So those guys invented variational autoencoders. So yeah, take a look at this paper. Okay, so let's take at the example here. So on the left, you can see a projection of TSNE of latent vectors from MNIST data. So MNIST is a data set of handwritten digits from 1 to 9. So you see that each of them are nicely clustered together. So since during the training, we learned the mean and standard deviation of each class, if you provide an input image from this cluster, let's say from the red cluster, like this is the zeros. So our model is going to know what digit it is, and it's going to guess the mean and standard deviation. So we will get something closer to the centroid, right? And then the model will randomly sample from this distribution and generate some new unique image that is within this standard deviation sigma. So variational autoencoder is able to generate unique data. All right, so this was variational autoencoders. So now let's move to transformers. So transformer-based models are very popular right now, and like all of the GPT models are based on transformers. So let's take a look. So transformers take as input sequence of vectors. So it was originally designed for textual data. So the way to represent the text is tokenization. So for example, it can be word tokenization. So each word will be a unique vector. And then once we convert the data to sets of vectors, we feed it into a transformer network. So the famous architecture is GPT and BERT. And the key component of transformers is multi-head attention. So each vector here in input is getting linearly transformed into 3 vectors, V, K, and Q. So they stand for values, keys, and query vectors. So then it goes to the linear layer and the scaled dot product attention. So here's the formula to get attention. So first, to get attention of I to J, you do a dot product of query I to the key J. So you multiply those vectors, and then it's getting normalized by dimensionality. And then the context vectors, the transformed vectors, that is output of the transformer, is computed as the sum over softmax of all of the attentions that are multiplied by the value vectors, right? So basically each transform vector is going to have the attention of all the vectors in the neighborhood. This is why it's called transformer, because it transforms each vector, right? And it transforms it in a way that it's getting attention of every other vector. So now you can ask the question, so what do we do with this? And so let's cover an example of BERT model. So during the training, we randomly mask some portion of the text in the sequence. So we call it mask token, which is a fixed vector. Then each vector in a sequence is getting transformed with this attention mechanism, and the mask token also is getting transformed. So we get output of the mask token, and then the transformed mask token we try to classify as the missing words. So we are trying to, from the mask, we try to predict what was the missing word. And in our case, the missing word was next. So whether in Miami next week. And using this random masking, if we provide a lot of textual data, then the model is going to learn the underlying distribution of the language, learn the patterns, and it's going to know what words should follow one another. Okay, so this was the pre-training part of the transformer. So the pre-training is done in unsupervised way. However, this is not enough to be a model for, let's say, prompt answering that the GPT is now doing. So yes, it is able to generate the text. So you can start with a prompt, let's say, like, tell me about Miami, and it will just guess all the next words in the sequence, right? However, it's probably not going to be accurate. So it's not going to give you a good answer because the model was not trained for question answering. So therefore, to make it great, like ChatGPT, we need to provide examples of those questions and answering. So what is usually done is that a pre-trained model is staying fixed. So we first, so during the fine tuning, we have some small subset of questions and the answers. So then we feed it the question, we feed it to the pre-trained model where the weights are fixed, the model is frozen, and then we transform each word in the question into the embedding vectors, right? So this is what transformer does. It transforms each word to the latent space. And then we feed it to the additional transformers. So here the weights are learnable, right? So usually this additional transformer is a lot smaller than the foundation model here that is marked in green, because during the fine tuning, we have a lot less data sets, and the left portion is already knows the language, it knows the pattern. So all we need to do is to provide a few examples of what we want to do, and then the model is going to adjust for novel questions that it haven't seen before. So then here the output will be, okay, tell me about Miami. Miami officially is the city of Miami, is the coastal metropolis, and the seat of Miami-Dade County in South Florida. So that could be the answer to this question. Okay, this was so this was the transformer-based models, and the next popular generative model is called diffusion model. So the idea is that to train such model, we step by step apply a Gaussian noise to the input data, right? So from this image of cat, we apply the Gaussian noise one by one, and up to the point when it's not distinguishable anymore. So it's just a noisy image. And then we train the network to denoise it. So we go in the reverse order. From the noise, we try to guess, okay, what was the image at the previous step. So we denoise it step by step, one by one, until we have the fine-grained image with a very high resolution. And so at each denoising step, we apply the denoising network. It can be autoencoder, it can be the transformer-based model, convolutional neural network, anything. So the unique component of diffusion model is that we denoise the Gaussian distribution until we have the nice resolution of the data. So if we have the data set that is sufficient enough, then once the model is trained, we can only provide this noisy image, and the model should be able to generate a clear image like this. So in fact, all famous models like Midjourney, DALL-E use combination of transformers and diffusion models. So this is an example of denoising step. So imagine that you have the noised version of the image. So how do we denoise it, right? So we can use the encoder-decoder architecture to predict the noise. So in autoencoder, we reconstruct exactly the same image, but now we're trying to guess what exact noise was applied to this particular image. And then we can subtract the noise from the input, and as the output, we will have the denoised version of this image. Thank you so much for listening. This is the end of the lecture. So here's the summary of what we covered. So first we covered the generative adversarial networks. So generator and discriminator is training at the same time. And what generator tries to confuse discriminator to classify real versus fake. Then in variational autoencoder, instead of deterministically generating latent vectors, so what we do is the model is trying to guess the statistics, the mean and standard deviation from the input, and then it randomly generates latent vector from this distribution, and it generates the image. So then we cover the class of transformer-based models. So transformer-based learns the data distribution through the attention mechanism. So we have the query key and vector representations, and then it's every vector in a sequence is transformed in a way so it has the attention of every other vector in the sequence. And to train the transformer-based model, you can do by masking some portion of the text and trying to predict what are the missing words. So large language models uses transformer-based mechanism. And then we learned about diffusion models. So it is trained by applying a noise to images, and the models try to denoise it such that it can generate new images completely from the noise. So this is it. This was overview of generative AI. Thank you for listening. I hope it was helpful to you. So let me know if in the comments what you understood, what you did not understand, so that I can correct my material. So subscribe and hit this this thing. Thank you. Bye.